welcome to my channel. So let's solve this problem. Actually, this is the second time because the first time is that I finished solving the problem, but then the mic wasn't even on when I watched the video, so I have to do it again. That's why there are writings here. So anyway, let's start. Okay, we have here a truss in which this one here is an isosceles triangle, and in which there are members inside this isosceles triangle. And here point A is connected through a pin joint while point B is connected to a roller. Now, at point C, there's a rope here which is connected to a mass on this inclined plane at an angle of 45 degrees. Now, this rope makes an angle of theta with the horizontal, and we are asked to find for the reaction forces at A and B in terms of T and theta. Uh, Not actually only T and theta, but we must write it in terms of actually it should be in terms of M and theta, because what's given here is M and theta, and of course this 45 degrees. Okay, to start with, we have to know this tension here. We have to solve this one first, because the tension here would be the same as the tension on this rope because they're connected in one rope, assuming that this is massless and this is frictionless. The pulley is massless and frictionless. Okay, so in order to do that, we have to construct an axis here such that the x-axis will be along the inclined plane. And by doing the summation of forces along x, you have minus t plus weight x. This is actually weight x, because when we tilted the axis, the weight now has two components, x and weight x and weight y. And if this angle is a, which is 45 degrees, this angle must also be a. So that clearly we have here our t is just equal to mg times square root of 2 over 2. Okay, now let's go over to the truss. We now know we can now express t as the given as mg square root of 2 over 2 times mg. Now let's look at the members. Let's simplify this one, because maybe some of the members are zero members, and clearly this very first one is a zero member, because this is these two vectors here, there, the one vector going from to here, and opposite vectors are linearly dependent. So this means that this one here is a zero member. Now if you remove this one, since this is a zero member, this will also be a zero member. Okay, if you delete this one here, and deleting this one would make this as a zero member, and so on. So the same goes with this other four members here, leaving only this. But since our t is applied here, this will be a zero member. Now, if the tension t is applied in any other points other than this, then some of these members will not be a zero member. You have to analyze it. Okay, so let's go solving this now. And let's assume first our reaction forces. In this case, the green now is our assumed. This one here, this one right there, going down, let this be to our AY. Our reaction force at A is A, in which it has two components, AY, and here is AX. This is our assumed direction. As for B, this green here is our assumed direction. Now B will not have an X component because this is a roller. Since this can move in this direction, so the only reaction force is vertical, unlike A, which has both horizontal and vertical. So we are now ready to calculate that. We have actually three unknowns, AX, AY, and B. But then we can generate two equations from here. Okay, so let's now start with the condition of global equilibrium. Since this is in static equilibrium, that means that the first condition of equilibrium states that summation of forces along X would be equal to 0. And of course, summation of forces along y would be equal to 0. This is the first condition of equilibrium. Now let's go over to the summation of forces along x. B will not have an x component, only the reaction force on A, because this is a pin joint. And T here will have an x component because here we are assuming that this is indeed parallel to this line here, to line AB. So here clearly fx is along the negative axis, that would be equal to minus ax plus tx in the positive direction equals 0. This would give us ax to be equal to tx is just equal to t of cosine theta. So this is just t cosine of theta. So we now have our ax. Okay, the next equation. Now notice here that, okay, this will be positive. This is ty, and ay is going down in our assumed direction, so that would be minus ay. And since b is going up, so that would be plus b equals 0. This would give us ay equals ty, which is t sine of theta plus b. Okay, now we still have two unknowns here. We already solved the first one. We need one more equation, and this second equation would be in the second condition, from the second condition of equilibrium, in which the summation of the moment at a point, at a pivot point, is 0 if we are in static equilibrium. Now let's choose the moment at A. Of course, the sum of the moment at A is 0, as well as the sum of the moment at C and the sum of the moment at B. But we are choosing this because if we choose B, we do not know the direction of A yet. What we know is the direction. What we exactly know is the direction of B and the direction of T. So let's do this. Now, the torque or the moment at A, due to this tension being applied to the point C. Now let's assume that this length, this is a blank L. Okay, so we know that the definition of the torque is just F cross L, cross product of force times the lever arm. In this case, our lever arm is going that way, and our torque, our force, is going this way, making an angle alpha with each other here. So that if we want to get the magnitude, that would just be FL sine of alpha. But what is alpha? Since this is theta here and this is 0, and we know that this is pi over 3, this whole angle here, because this is an isosceles triangle. So that this all these angles are actually um, pi over 3. So that this would make alpha as pi over 3 minus theta. So this means that, okay, we have t times L sine of alpha, okay, and we're taking the we're taking the clockwise rotation as the positive direction. Now B would cause a counterclockwise rotation, so that's why this must be negative. Okay, a negative torque. So that would be B times L. What's the angle between B and the lever arm? That's 90 degrees. So this is just 1, and this is equal to 0. Now L will cancel out. That means that our answer will be independent of the length um, of the truss. Okay, so from here we would know that B is just equal to T sine of pi over 3 minus theta. But what is this? This is just the difference of two angles. Okay, so we can get that. Okay, we have this, we can solve actually that sine of pi over 3 using the trigonometric formula of the difference of two angles. For sine, this would give us square root of 3 over 2 cosine of theta minus half of sine theta. So we now have a value for B. B now would be equal to square root of 3 cosine of theta minus sine of theta over 2 times t. So we have solved V. Now, let's substitute later the value for t, which is this one here. So We'll just use t for now to shorten our notation. Okay, now in which direction is b going? Since we don't have a value here, then we must actually analyze this. Uh, we must actually analyze the range of the values. Okay, we know that t is always positive here. Of course, it's an absolute value. We're taking it as an absolute value. Now, cosine t and minus square root of 3 minus sine t. Now, since our force is assumed to be acted on this region alone, from theta equals to 0 to theta equals to pi over 3, meaning that for theta less than equal to pi over 3 but greater than or equal to 0, we will be sure that square root of 3 cosine of theta is greater than or equal to um, sine of theta. This would mean that this is always positive. So in this case, since we get a positive b, then the true direction of the force of the constraint force at B is the same that with our assumption. So this is in blue. The blue is the true direction. So it's the same. Okay. So we now have B. We can now solve for AY. And once we now have AY, we can solve for A. Okay. So AY is just equal to C T sine of theta plus B. So we have here T sine of theta plus B plus this one here. We have square root of 3 cosine of theta minus sine of theta over 2 times t, and we multiply this by 2 over 2 so that we can combine the fractions. So this would give us now um, cosine of theta minus sine of theta, because they have 2t here. We have no plus sine of theta. So ay, okay, would be equal to square root of 3 cosine of theta plus sine of theta over 2 times t. Okay? And that's it. Now, clearly, this is positive for all theta from 0 to pi over 3. So, clearly, our assumed direction is the same as the true direction, the blue one. Okay? And clearly, our x also in this case is positive. So, this is the correct direction. So that our A reaction force at A is going somewhere in the, let me use red for that, or I'll use which one? Green. It's going somewhere in the third quadrant. That would be our reaction force A. Okay, so let's take the magnitude of A, in which A, that is just equal to A squared is equal to AX squared plus AY squared. So A squared would now be, take the square of that, we have t squared cosine squared theta plus the square of this. We would have now 3 cosine squared theta plus 2 square root of 3 sine theta cosine of theta plus sine squared of theta over 4 times t squared. Now we multiply 4 over 4 here so that we can combine. And it's actually better if we can, well, we'll just use this. Okay, so simplifying this further, we would see that our cosine would be 4 plus 3, that would be 7. And uh, okay, let's remove this one here. We'll take this as 2 cosine squared plus cosine squared, because there's a sine squared here, and cosine squared plus sine squared is 1. So that we have 4 plus 2, the remaining part of this one would be equal to 6. So we have 1. So this is indeed 1 plus 6 cosine squared theta plus 2 square root of 3 sine theta cosine of theta over 4, okay, times t squared. This will be our a squared, okay, or we take our A as, take this 2 here and take the square root, that would be our A. Now, if we multiply, now we will now solve for A and B by substituting now this value for tension, mg over 2. Okay, this is there is square root over 2 over square root of 2 over 2 here, so you would have square root of 6 plus square root of 2. No, not ay. Let's solve b. Yeah, this is square root of 2, so this is square root of 6 minus square root of 2 in that sense here. So okay, first let's solve a. Okay, a now would be, okay, square root of 2 over 2. Square root of 2 over 2, let's take square root of 2 inside, and there's a 2 here. So that means this is just 2 times 1 plus 6 cosine squared theta plus 2 square root of 3 sine of theta cosine of theta square root over 4 times mg. While our b would be, this is square root of 2 over 2, that would be square root of 6 cosine of theta minus square root of 2 sine of theta over 4 times mg. Okay, so this now are our final answers for the constraint force. Okay, now let's investigate this much further. What if our tension is, instead of having an angle theta, we take it straight in this direction? Okay, so we might want to solve for that one. Okay, so to do that, if that okay, so to do that, if this is our t, in this case, let's just assume that, okay, it goes this way, that one. So this would make us as our theta to be equal to pi over 2. In this case, what would happen to our, okay, let's solve ax. Ax now would be equal to 0 because cosine of pi over 2 is 0. How about ay? Ay would become this. This is our ay. This is 0. And this is just 1, sine of pi over this 1. So this is just equal to t over 2. While our b would be equal to, or yeah, if it's just you can substitute mg over 2 here, and our b would just be equal to, um let's look at b here. This is 0, and as we can see, b now becomes negative t over 2. What happened? Why is it negative if we set t tension in this case? Well, this must be the case because if there's a force going up, then the support, this is the triangle, this supports here, it must also have a downward force to equate this force going up. And as you can see, the magnitude is the same. By the way, the B in our previous one, for any theta here, it's going up. But when we set theta to be equal to 0, it's going down. In fact, actually, you will see that for theta greater than pi over 3, B will start to be negative. It will start to be on the negative direction, on the downward direction. That's why this becomes negative here. And it is expected that it's t over 2 because of symmetry. Okay, because of symmetry, then this one will go, okay, because of symmetry, then they will just divide it equally into two parts. Okay, that's why we have that. How about when tension is going this way? Well, we cannot imagine, well, we can just hang the mass here of uh, anyway, if t is going that way, let's forget about this. Let's just take any t, such as the same magnitude of t is as like this one. So what would that would give us a theta of equal to negative pi over 2, because this is our rotation on the clockwise direction. Ax would still be 0, and ay would be still ay. Okay, look at ay. This is negative, sine of negative pi over 2 is negative 1. So ay would still be t over 2. Sorry. Ay would be, okay, ay would become, this is our ay. So this is negative 1. So this is negative t over, so ay would be negative t over 2. Okay? And our b would be equal to, this is negative 1. So this is just t over 2. So what happened now if we apply the force in this direction, then these two reaction forces must go up, and they must be the same. I mean, they must divide this force here equally into 2. And that's why our A becomes negative, because our assumed direction is right here. And we get a negative when we shift to this, when theta equals negative pi over 2, so it goes up. And B still is positive. In fact, all throughout here, we are sure that B is positive. Okay, now let's, okay, so these are two special cases. Another special case is that when theta equals 0, it's going this way. Okay, when theta equals 0, ax would just be equal to t. And ay, what is ay? Ay would be, this is square root of 3 over 2t. This is equal to square root of 3 over 2 times t. It's positive. And what would be our b? B would be equal to, this is 0, and that is just square root of 3 over 2t. And okay, so meaning this is actually that here we have ax and we have ay, and a is actually going this way also, while t is going still on the positive. We're done now with the reaction forces. Let us now calculate the forces on the members. So the members that we will be considering is only these members here: AC, AB, and BC. Okay, because all of the other members inside this will be are zero members. Okay, so all the forces here are 0. So okay, let's calculate AC first. Okay, okay. So in this case, this one, okay, since we know that this is our A, that would be our A there. Our A, let's assume that our AC is going this way. So that would be AC. And AB would be going this way. I'll just use green. This is AB. Okay, I'll just use blue here. Okay, this is my assumption. Now let's calculate now AC. To do this, we actually use the vector equation. Okay, summation of forces at point A along X. Summation of forces along X at point A. That would be equal to, what are the forces along X? We have ACX plus AB. AB has no Y component, so let's just use AB here. And minus AX equals 0. We already have our AX. This is our AX here, right here. Okay. So we don't have AB yet. We have two unknowns actually here, AC and AB. Now the next equation would give us would be summation of forces along Y at point A. What are the forces along Y? We have ACY minus AY equals 0. AB has no Y. So this is our AY here. That would be our AY. Okay. So that clearly ACY is just equal to square root of 3 cosine of theta plus sine of theta over 2 times t. Okay, but since ACY is just AC cosine of, this is pi over 3 here. So AC, not cosine, AC sine of pi over 3, sine of pi over 3 square root of 3 over 2. So this is just equal, actually, this is just actually equal to, we can write this as square root of 3 over 2 AC. That would make our AC to be equal to uh, okay, square root of 3 cosine of theta plus sine of theta over square root of 3 times t. And of course, we can just substitute this one to t. Okay, as for now, let's just use this one. Okay, so we now have value for AC. We can now calculate AB. And AC is positive, meaning it's really going that way. So clearly, that one there, CA is going the opposite way. So we can see that that this is suffering, this one here, right here, is suffering from a tensile force. So this is tension right here. Why is it tension? Because uh, if dirt, actually, because the tension, the T here, the force T is actually, we're trying to stretch this member right here. And in order for not to stretch, this member has to exert a force on this direction. Okay, that's why we know that the tension, that it's actually ongoing tension right there. Okay, now how about, okay, we how about AB, how about BC? Okay, now here is negative of AB. We know that this is just negative of AB. And okay, uh we can calculate AB first. AB is, what is AB now? AB from this one is just AX minus ACX. What is ACX? Again, that is just AC cosine. Okay, cosine of pi over 3, which is 1/2. So this is just equal to 1/2 of AC. So this would give us T cosine of theta minus a half of AC. So this is square root of 3 cosine of theta plus sine of theta over 2 square root of 3 times t. Now we can combine this by multiplying 2 square root of 3 here over 2 square root of 3. So we can combine 2 square root of 3 minus square root of 3, that is just square root of 3 cosine of theta. And this is plus sine of theta over 2 square root of 3 times t. This is now our AB. Okay, this is positive. So meaning that right here, it's really indeed going this way. The same with our assumption. So this one right here is also undergoing tension. Okay. Now we can now calculate um, BC. Okay. By the way, what is our B? B is, this is our B. Okay. This is B, while this one is our BA. Now, of course, it will be um, of course that this force right here must be on this direction. Okay, so let's this is now our BC. Okay, we can now calculate BC by using BC is just actually the negative. As we can see, we can go directly with the because this is BC if we take BAX plus B. Okay. Now, as we can see, BC must be equal to, if this is negative BA I hat plus, or we have minus B J hat. Okay. So in fact, we now have the value for BC. Okay, this is our BCX. So our BCX is just equal to BA negative of BA. But negative of BA is just equal to AB. So this means that this is just equal to the okay, AB. Uh, this is equal to this. So square root of 3 cosine of theta plus sine of theta over 2 square root of 3 times t. Okay? And how about our BCY, which is negative B? Our B is this, so negative B is just reverse this, the sign. So this would be give us sine of theta minus square root of 3 cosine of theta over 2 times t. Okay? We can actually calculate BC as the square root of the sum of squares of this. When we square this, we get 3 cosine squared theta plus, okay, this is quite long, 2 square root of 3 sine of theta cosine of theta plus sine squared of theta, okay, over 4 times 3, that would be 12 t squared, plus squaring this one, we get sine squared theta minus 2 square root of 3 sine theta plus cosine of theta, sine theta cosine of theta plus 3 cosine squared theta over 4 times t squared. Okay, we can combine this by, um, this is 12, so we have to make this 12 here, so we have to multiply by 3, so this becomes 3, this will become 6, and this will become 9. So we can now add cosine squared. We have 9 plus 3, we have 12. 12 cosine squared theta, and this is 2 minus 6 square root of 3, so this is minus 4 square root of 3 sine theta cosine of theta plus 3, we have sine squared is sine, 1 plus 3, we now have 4 sine squared of theta over 12 t squared. Or if we simplify this, that would just be, this is 3, yeah, that would be 3. 4 cosine squared minus square root of 3, uh, no, not 4, this is 3, okay, minus square root of 3 sine theta cosine theta plus uh, sine squared theta over 4 t squared. And what we have here is, this is, I think this is a perfect square. This square root of 3, okay, this is just equal to square root of 3 cosine of theta minus sine of theta squared over 4 t squared. I think this is correct now. Wait, sorry. This is not 4, this is 3. Okay? That would be 3. Okay? So, again, we now have our BC. Our BC would be, okay, I'll just write BC here. It would give me square root of 3 cosine of theta minus sine of theta over square root of 3 times t. So these are our, okay, BC, AB, and AC. And BC is going this way. CB is going that way. And it's actually because we have a tension and applied force in this direction. This is our T. Okay? This will be our T. This is now in compression. This side here will be in compression. Okay? So we now have we now have solved this. Okay, let's write in this case we can actually, okay, we can say that this is a tensile force in this case. This is in, how do I write this one? This is in tension. This one is also in tension, whereas this one is in compression. And why is that? We can actually just use our intuition why this one is. Because as you can see, as you take this one into, as you try to rotate, no, apply a force, this will be compressed because there's a force acting on that. This will be compressed. And since this will be stretched because there's a force that's preventing it to move. So this part will be stretched, okay? And this part also will be stretched because we're trying to rotate, okay? This one, given the pivot is B, okay? So that's why this is in compression, tension, and tension. So this solves us our problem. Okay, I think we have done it all. Okay, our T here will just replace T here by just mg, square root of 2 over mg. Okay, and we now calculate our BC. Now let me know if there's something wrong that I have done algebraically here because I haven't solved this. I mean, I solved it a while ago, but I already forgot what I got. So I solved it impromptu on the spot. So maybe the signs I was mistaken on that. Okay, just let me know in the comments so that it can be corrected. Okay, so these are the forces on this one. Okay, by the way, I'll give you something that you can do on your own, but this is actually for fun. Okay, so we have not actually calculated this portion here. So okay, let's draw that again. And we know that AC is going this way. That would be AC. And BC, okay, or let's call this CA. This is CA. And let's call this CB. And we have the tension right here. We have the tension T, which makes an angle of theta. So this is T. Now, you can show on your own. Where's my... Okay, you can show on your own. You put the axis here. This is the x-axis right there, and the y-axis. Show that the sum of these vectors, okay, show that CB plus CA plus T equals 0, meaning this would actually give you two equations: the forces on the along x, summation of forces along x, which is equal to 0, and summation of forces along y equals 0. Okay, just take note of the angle. Since this is 60 degrees or pi over 3, this must also be pi over 3, and this is pi over 3, so this must also be pi over 3. Now you can show this, that this adds up to 0. This should, because we are in static equilibrium. Okay, uh, by actually using this 3. Okay, so that would be all. Thank you for watching. Enjoy solving.